This question looks at ions and complexes. Part A. You're provided with boiling tubes containing solutions of the same ionic compound. The compound contains one cation and one anion from the lists below. Solutions of common laboratory reagents are available. Plan a series of tests that you could carry out on the samples to identify the ionic compound. Your test should produce at least one positive result for each ion. For each test, include details of reagents, relevant observations, and equations. Explain how your observations allow the ions to be identified. You may include flowcharts or tables in your answer. If we begin with the tests for the different cations we're presented in the question, we can set this out as a table with cations, the test, and the result. We have three different cations that we're presented. We have Mn2+, Fe2+, and NH4+. We're going to test each of these with aqueous sodium hydroxide, so I'm writing NaOH just to simplify the sodium hydroxide. With the NH4+ ion or cation, you need to have some gentle heating. This is some detail we're including in the question because they've asked for any relevant details. Now let's look at the results for each of these cations with the test we're using here. Mn2+ will result in a pink precipitate, Fe2+ will result in a green precipitate, and NH4+, if you held litmus paper over the boiling tube, the litmus paper would then turn blue. Next, we need to write the relevant equations for the cation tests. If we start with Mn2+, if we're adding two OH- ions from our NaOH, we would then result in MnOH2. This is the same equation for Fe2+, so Fe2+ plus 2 OH- goes to FeOH2. For NH4, we're adding one OH- ion, and that's going to result in us forming NH3 or ammonia and water. Now we're going to look at our anions and our tests for our anions in the question. So we're going to lay this out as a table with the anion, the test, and the result. We're given three different anions, a carbonate ion, a sulfate ion, and a chloride ion. We're going to then test the carbonate ion with nitric acid, the sulfate ion with barium nitrate, and the chloride ion with silver nitrate. We're going to then write the results, so the carbonate ion will react with nitric acid and it will effervesce, which means to bubble. Then both the sulfate and the chloride ions will react to form white precipitates. Now we need to write the equations, so we're going to have the carbonate ion react with H+ to form H2O and carbon dioxide, H2O meaning water. Then we're going to have our sulfate ion react with barium 2+ to form barium sulfate, which is the white precipitate we've recorded as our result. Finally, we're then going to have our silver +1 or Ag+, and our chloride ion or Cl- react to form silver chloride. Next, we're going to add some detail to our tests for the anions. So like we've done with the cation saying gentle heating for our ammonium ion, we need to say that we need to add some dilute ammonia to the chloride ion test, and that means that the precipitate will then dissolve. Also, we need to specify that we're going to conduct all of these tests in separate boiling tubes. That means that there's going to be no contamination between any of the anions or cations or the test reagents. They're not going to react with each other, and that means that our results are genuine. To get the 6 marks for this question, you must develop a plan that allows identification of all 6 ions and includes essential detail and equations. For all test procedures and observations with 3 anion tests in correct sequence or in separate boiling tubes as we've stated here. We must also include a cation test with essential detail and all equations, which we have done in this model solution. Part B. The dissociation of water is measured by the ionic product of water, Kw. The value of Kw varies with temperature as shown in the graph below. Calculate the pH of water at body temperature 37 degrees Celsius. Firstly, what we need to do is read off the graph at 37 degrees Celsius and find our Kw value of 2.4 times 10 to the negative 14 moles squared decimeters to the minus 6. So our Kw value, if we quickly jot this down, is 2.4 times 10 to the negative 14, and that's because of the units of the graph, moles squared decimeters to the minus 6. Then we're going to use the equation Kw equals H plus squared, and that's because we're assuming that H plus and OH are the same concentration. So that's another way of writing this equation. So if we then want to find H plus, we would need to square root Kw, which is 2.4 times 10 to the negative 14. And that equals 1.55 times 10 to the negative 7 moles per decimeter cubed. Then, using the equation of pH equals minus log 10 H plus, we can find the pH of water at body temperature. So that would be pH equals minus log 10, 1.55 times 10 to the negative 7, and that equals 6.81 to 2 decimal places, which we then write on the answer line provided. And here where I've starred Kw, the reason why we can assume that the concentration of H plus equals the concentration of OH minus is because the solution is not overly dilute or acidified. To get the marks for this question, you get a mark for correctly reading off your Kw value from the graph, so that can be anywhere between 2.2 and 2.4 times 10 to the negative 14. You get a mark for then working out your concentration of H plus correctly, so rooting this and getting 1.55 times 10 to the negative 7 if you use 2.4 times 10 to the negative 14. And then you get your third mark for correctly working out pH. So in this case, that would be 6.81 to 2 decimal places. Part C. A complex of cobalt has the following composition by mass. Cobalt, 21.98%, nitrogen, 31.35%, hydrogen, 6.72%, chlorine, 39.75%. Part 1. Calculate the empirical formula of this complex. When working out empirical formula, we need to take the percentages we've been given, or the composition by masses, and divide them by the relative formula mass of each element. So let's start with cobalt. So for cobalt, we have 21.98 divided by its relative formula mass, 58.9, and that equals 0.373. Then for nitrogen, we have 31.35 divided by its relative formula mass, 14. That equals 2.24. Then for hydrogen, we have 6.72 divided by its relative formula mass of 1, which equals 6.72. And then chlorine, which is 39.75% divided by its relative formula mass of 35.5, gives us 1.12. Then we need to divide by the smallest. So we're going to do 0.373 divided by 0.373. That equals 1. Then we have 2.24 divided by 0.373. That gives us 6. Then we have 6.72 divided by 0.373. That gives us 18. And chlorine, 1.12 divided by 0.373 gives us 3. So that means the empirical formula is CON6 H18Cl3. To get the 2 marks for this question, you get your first mark for correctly dividing by the relative formula mass, and your second mark for then dividing by the smallest to give the correct empirical formula. Part 2. The formula of this cobalt complex can be expressed in the form COLM X plus Cl minus N. Suggest the chemical formula of COLM X plus. So in the empirical formula we have 3 chlorines. So in the form we're going to have chlorine and N will equal 3. That means the value of X has to be 3 plus in order for it to be a balanced complex. So then we're left with our nitrogens and hydrogens. So the L in this complex will be CONH3. So ammonia will be our ligand. And then we're going to write 6 as our value for M, and then our 3 plus charge. To get the mark for this question, you must correctly write the chemical formula CONH3 6 3 plus.